In this lesson, we're going to introduce vector algebra by first defining what position and displacement vectors are. In a Cartesian plane of origin O, if defined by an orthonormal system, it would consist of two perpendicular axes and a unit vector I along the horizontal axis and a unit vector j along the vertical axis equal in length to vector I as the system is orthonormal. The importance of the unit vectors is that the direction defines the positive sense on the axes. For example, the unit vector I is oriented to the right, then the positive sense on the horizontal axis is to the right side. And the length of the unit vectors define the scale or the length of each unit on each axis. And in this case, the unit vectors I and j having the same length implies that we're considering equal scales on both axes, while the work that follows would exactly be the same if we were to be working on different scales. Now, to define the position vector of a point, if I'm given, for example, a point M of coordinates -2 and 3, to plot point M, I move horizontally twice the vector I in the opposite direction, as the abscissa of M is negative, to get to point P, and 3 times the vector j in the same direction, as the ordinate of point M is positive, and to get to point Q. What is the sum of vectors OP and OQ? By the parallelogram law, the sum would be vector OM, where M is the fourth vertex of the parallelogram. Then vector OM can be written as -2 times the vector I plus 3 times the vector j. And O being the origin of the system, then vector OM would define the position vector of point M as it defines the position of M with respect to the origin O. To generalize, if I'm given a point M of coordinates x and y, then on the coordinate system, pointing out x on the horizontal axis and y on the vertical axis, and plotting point M would define the position vector of point M as vector OM equals to x times I plus y times j. As for displacement vectors, if I'm given 2 points A and B with respective coordinates 2, 4, and 4, 1, for example, plotting the points on a coordinate system, vector AB would be a displacement vector as it shows the displacement from point A to point B, forming the right triangle with AB at the hypotenuse. The horizontal displacement is 2 units in the positive sense, while the vertical displacement is 3 units in the negative sense. By the triangle law, vector AB would be equal to 2 times vector I and -3 times vector j. However, the horizontal displacement 2 is in fact obtained by subtracting x of A from x of B, which in this case would be 4 minus 2. And the vertical displacement -3 is obtained by subtracting y of A from y of B, which in this case is 1 minus 4. Then vector AB can be written as x of B minus x of A along vector I, and y of B minus y of A along vector j, or as an ordered pair where vector AB would have x of B minus x of A and y of B minus y of A as components. However, in 3D, given an orthonormal system, OIJK, represented by 3 axes perpendicular 2 by 2, along with their unit vectors, in this case I, j, and k. The x-axis is the axis directed by vector I, called the axis of abscissas. The y-axis is the axis directed by vector j, called the axis of ordinates. And the z-axis is the axis directed by vector k, called the axis of elevation. For simplicity and to visualize better, we are going to work without the negative part of the axes. Now, given point M of coordinates x, y, z, the position vector is defined similarly as in 2D by OM equals to x times I plus y times j plus z times k. And that is because if we move by x units along I, and y units along j and z units along k, then in the xy plane we complete the parallelogram to retrieve the vector sum. Then we elevate it by z units to retrieve the position of point M, which leads to the position vector OM as follows. And regarding displacement vectors, any displacement vector between 2 points, let's say A and B, would be defined similarly by the components x of b minus x of a, y of b minus y of a, and z of b minus z of a along each of the unit vectors.